In this video, we will continue our study of fluids at rest. I will describe Archimedes' principle and apply it to buoyancy. Buoyancy is defined as an object's ability to float in a fluid. For example, wood floats on water and helium floats air. Buoyancy also explains why objects feel lighter when submerged underwater or another fluid. A buoyant force acts on objects submerged in fluids, which causes objects to float or even feel lighter. A buoyant force is an upward force that acts on an object submerged in a fluid because of the pressure gradient or pressure difference within a fluid. To prove that there is in fact a buoyant force within fluids, we must remember that it varies with depth. The closer to the surface, the lower the pressure, and the further from the surface, the pressure is higher. To demonstrate the origin of the buoyant force, let's consider a cylinder-shaped object placed within a fluid. The cylinder has a surface area A both at the top and the bottom. Because the bottom of the cylinder lies deeper within the fluid, the pressure, P2, on the bottom is greater, and therefore the force, F2, acting on the bottom is greater. F2 can be calculated using the formula P2 times A because pressure equals force divided by area, or force equals pressure times area. But pressure at a depth is equal to rho GH, where H in this case is height 2, or H2, beneath the surface. So F2 is equal to H2 times rho GA. Similarly, a force acts at the top of the cylinder. However, because the top of the cylinder lies at a lesser depth, the pressure, and thus the force on the top, is smaller. F1 can then be calculated using the formula P1 times A, where P1 is rho GH1. Therefore, F1 equals H1 times rho GA. Because there's a difference in pressure above and below the cylinder, as well as a difference in force above and below the surface, we can say that a net force exists on the cylinder in the upward direction because F2 is greater than F1. So we call this net upward force a buoyant force, F sub B, which is the difference between the force upward, F2, and force downward, F1, or FB equals F2 minus F1. Plugging in the formulas for F2 and F1, we get rho GAH2 minus rho GAH1. We can factor out the rho GA, and we're left with H2 minus H1 in parentheses. But H2 minus H1 is known as delta H, so we can replace what is in parentheses with delta H. But area times height is known as volume, so we can replace A delta H with V, the volume, and we find that buoyant force is equal to rho Vg, where rho is the density of the fluid, that's why we have the sub F, and V is volume of the fluid displaced, again why we have the subscript F, times G. Now we can then combine density times volume, because density times volume is mass, and this is mass of the fluid. So we find that buoyant force is equal to the weight of the fluid displaced. Archimedes' principle states exactly that. The buoyant force on an object immersed in a fluid is equal to the weight of the fluid displaced by that object. But you might be wondering how much fluid gets displaced by an object. This was illustrated in a simple experiment performed by Archimedes, in which an object is placed in a beaker filled to the top with a fluid. When the object is placed in the fluid is displaced, or the level of the fluid would rise. But because the beaker is already full, the fluid overflows. The volume of the fluid that overflows is equal to the volume of the object that was submerged. This means that the volume of the object that's submerged is equal to the volume of the fluid displaced. For example, think about when a person steps into a bathtub. When their body is immersed into the water level rises by some amount. The amount of water that's displaced, or that rises, is equal to the volume of the person's body that's underwater. If a person places only their hand in water, the water level would rise by an amount equal to the volume of their hand. Also, if a person immerses half their body in the water, then the water level would rise by an amount equal to the volume of half of their body. And again, as you can imagine, if a person immerses their entire body in the water, then the water would be displaced by an amount equal to the volume of their entire body. This relationship is sometimes used to determine body fat percentage for humans. When an object floats, there must be an upward force, the buoyant force to counteract the downward force of gravity, or weight. If the object is floating up to the surface at an accelerating rate, then the buoyant force must be greater than the weight. But what if an object sinks? An object that sinks actually still experiences an upward buoyant force. If the object is sinking at an accelerating rate, then the weight must be greater than the buoyant force. What if the object floats or sinks at a constant speed? How does the magnitude of the weight relate to the magnitude of the buoyant force? Well, objects moving at a constant speed are considered to be in a state of equilibrium, and therefore the weight must be equal to the buoyant force. Remember, this is only true for objects moving at a constant speed. You may also remember that density is related to whether an object floats or sinks, and thus determines how buoyant an object is. Objects float if its density is less than that of the fluid. As another general rule, objects sink if its density is more than the fluid. And objects flink if its density is equal to that of the fluid. No, that's not actually a word. The object would neither float nor sink. It would actually remain submerged underwater, stationary within the fluid. So density does influence the buoyancy of an object. What does it mean for an object to float? And I don't mean floating as in rising up to the surface. I mean floating as in already at the surface and sitting at the top of the fluid. If the object is sitting at rest at the surface of a fluid, then it's in a state of equilibrium, or the net force equals 0. Weight acts down on the object, but the buoyant force acts up on the object. Because these are the only two forces, then the buoyant force equals the weight of the object. So F sub E equals mg. Plugging in the formula for buoyant force on the left side of the equation, rho Vg, where this is density of the fluid, volume of the fluid times g. And then on the right side of the equation, plugging in mg, where m can be replaced with density times volume, and this is density of the object times volume of the object times g. We then can cancel g out of either side of the equation and rearrange so that we have volume of the fluid divided by volume of the entire object equals density of the object over density of the fluid. The left side of this equation F over V naught, or volume of the fluid displaced divided by volume of the whole object, is basically telling us how much of the object is actually submerged in water. So, this tells us that the fraction of the object submerged is given by the ratio of the object's density to that of the fluid's density. We can apply all of these ideas to a submarine's ability to rise, sink, or float within a fluid. Take a look at picture 1, all the way to the left. If a submarine is to dive, then its weight must be greater than the buoyant force. In order to increase the weight of the submarine so that it becomes greater than that of the buoyant force, the submarine pulls water into its tanks. This increases the density of the submarine and thus increases the weight. This causes the submarine to accelerate downward. Picture 2 in the lower right shows that to make a submarine float or remain at a constant depth, its tanks are filled until the density of the submarine is the same as the density of water. Because of this, the weight of the submarine equals the buoyant force, and the submarine will remain at rest or move at a constant speed up or down. Picture 3 on the upper right illustrates how to make a submarine rise. Compressed air is blown into tanks, forcing the water out. This decreases the density of the submarine and makes it weigh less than the buoyant force. This may make more sense to you if you've ever gone underwater with lungs full of air and then released some of the air in your lungs through your nose or your mouth. You may have noticed that your body actually begins to sink further into the water because your weight is greater than the buoyant force upward. As another general rule, objects will float to the surface if the weight is less than the buoyant force, or if the object is less dense than the fluid, or an object decreases its mass to become less dense than the fluid, or an object increases its volume to become less dense than the fluid. In contrast, objects sink below the surface if the weight is more than the buoyant force, the object is more dense than the fluid, the object increases its mass and becomes more dense than the fluid, or the object decreases its volume and becomes more dense than the fluid. You may also have experienced that objects immersed in a fluid seem to weigh less than when lifting them outside of the fluid. For example, lifting a heavy rock outside of water is difficult, but when the same heavy rock is immersed fully in water, it's actually easier to lift. This is because the apparent weight is actually different than the actual weight. They are not equal to each other. Remember, apparent weight is what the object appears to or seems to weigh. The apparent weight of an object is less than the actual weight of the object because when an object is submerged in a fluid, the buoyant force assists in acting against gravity. So if you're trying to lift a rock underwater, gravity pulls down, but there's also a buoyant force upward that's helping you lift the rock. So it seems as if it weighs less than it actually does. The diagram shown illustrates both Archimedes' principle and apparent weight. First, a 5-kilogram object is hung from a scale. The spring scale reads the actual mass, 5 kilograms, which is 49 newtons. In the second picture, notice the object has been immersed in the fluid, or submerged, and this caused the water to overflow through the opening into another container. This is because placing the object underwater causes the water level to rise or to be displaced. The water that was displaced or overflowed has a total mass of 2 kilograms or 19.6 newtons. The buoyant force acting on the 5 kilogram mass is actually equal to the weight of the fluid displaced, which is 19.6 newtons. This upward force counteracts the actual weight, and therefore the spring scale should read 49 newtons minus 19.6 newtons, which is 29.4 newtons, or converting this to mass, 3 kilograms. This means that the buoyant force will behave in such a way that the 5 kilogram object has an apparent mass of 3 kilograms, which is actually 2 kilograms less than the actual mass. It may also be helpful to describe the same concept using free body diagrams. When a 3 kilogram object hangs from a spring scale, the weight, mg, is 29.4 newtons, and it's a downward force. Because the mass is at rest, the spring scale provides an upward force equal to the weight, also 29.4 newtons. So in our first free body diagram, we can see that because the mass is at rest, or in a state of equilibrium, the equals the reading on the scale, which is 29.4 newtons. Now, the same 3 kilogram mass is placed into water. The actual weight remains the same, as we can see in our free body diagram, it's still 29.4 newtons downward. However, the spring scale measures apparent weight, which is now 19.6 newtons. This means the water must provide the additional 9 newton force upward, the buoyant force, so that the object remains at rest and thus in equilibrium. So in our second free body diagram, we can see we have weight down, 29.4 newtons. We have the buoyant force up, assisting in lifting the object, 9.8 newtons, and this means that the scale reads the difference in the two, which is 19.6 newtons. Let's try some practice problems. The specific gravity of a piece of wooden block is 0.5, whereas that for gasoline is 0.68. What fraction of the wooden block is above the surface of gasoline when the wooden block floats in gasoline? Pause the video for time to work on the solution. We were told in the problem that the specific gravity of wood is 0.5, which means, converting it to a density, 500 kilograms per meter cubed. The specific gravity of gasoline is 0.68, and converting that to a density, we get 680 kilograms per meter cubed. If you forgot how to calculate density from specific gravity, make sure you check out video 1. Using our equation, which relates the density of the object to the density of the fluid, we have volume of the fluid displaced divided by volume of the object equals density of the object divided by density of the fluid. Remember that volume of the fluid displaced divided by volume of the object is really the fraction of the object that's submerged under the fluid. So, if we take the right side of the equation and plug in density of the object, the wood, 500 kilograms per meter cubed, and divide by density of the fluid, gasoline, 680 kilograms per meter cubed, we get 0.735. Now, 0.735 as a fraction is 25/34. That means that there is 25/34 of the object that's actually submerged underwater, under the gasoline. Because we're looking for the fraction of the object that's still above the fluid, we say the whole object is 1 or 100% minus the decimal that represents how much is under the fluid, and we get 0.265, which is 9/34. That means 9/34 of the object is still above the gasoline. As percentages, 26.5% of the wood is sitting above the fluid, and 73.5% of the wood is actually below the fluid, to make a total percent of 100. Let's try another practice problem. A 2 kilogram copper block has a 1.7 kilogram apparent mass when submerged in a fluid. What is the density of this fluid? The density of copper will be given to you, and it is 8,900 kilograms per meter cubed. Pause the video for time to work on the solution. It is helpful to begin with a sketch and/or free body diagram. The copper block experiences 3 forces: a weight down, the buoyant force up, and an additional force up, which we will call the normal force, assuming that the block is actually resting on a surface. However, this upward force could also be caused by a spring scale and would be considered tension, or even a pulling force by you if you were trying to lift the object. We begin by stating that the net force acting on the object is equal to 0 because the object is in a state of equilibrium or is sitting at rest. Writing out net force in terms of the individual forces, we add the buoyant force plus the normal force minus the weight because it's acting downward, and set that equal to 0. We're told the apparent mass is 1.7 kilograms, meaning that the apparent weight is 1.7 kilograms times 9.8 meters per second squared, which is 16.6 inches. And recall from some of our past units, apparent weight is identified as the normal force. The actual weight is equal to mg, where m is 2 kilograms and g is 9.8 meters per second squared, so we get weight of 19.6 newtons. We still want the buoyant force, so buoyant force, rearranging our original equation, we get weight minus normal force, or 19.6 newtons minus 16.66 newtons, and we get 2.94 newtons for the upward buoyant force. But buoyant force is equal to density of the fluid times the volume of the fluid times g. And it's also known that volume of the fluid displaced is equal to the volume of the object, and volume of an object is equal to mass divided by density, or the 2 kilogram mass divided by the density of copper, which is 8,900 kilograms per meter cubed. And we find the volume to be 2.25 times 10 to the minus 4 meters cubed. We have our buoyant force, 2.94 newtons. We set that equal to density of the fluid times the volume of the fluid times g. We have g, and we now have the volume of the fluid, so we should be able to solve for the density of the fluid, and we get 1,335 kilograms per meter cubed. Now, before we go on, does it make sense to have the density of the fluid be lower than the density of copper? It should, because copper is in fact sitting at the bottom, or has sunk to the bottom, and in order to sink, the density of the copper must be greater than the density of the fluid, and this works out. Problem number 3. A 0.4 kilogram beaker containing 1.2 kilograms of water rests on a scale. A 2 kilogram block of gold is suspended from a scale and completely submerged in the water as shown on the left. Find the readings in kilograms of the top scale and then B, the bottom scale. Pause the video for time to work on the solution. Again, it's helpful to begin with a free body diagram. We'll start with the top scale, or the object that's hanging from the top scale. The object has a weight down, a buoyant force up, and a tension up, and we'll call this T subscript SS for spring scale. This is the tension provided by the spring. In the problem, we're given the specific gravity of gold, 19.3. Converting that to a density, we get 19,300 kilograms per meter cubed. Because the gold block is hanging at rest within the fluid, then we can say it's in a state of equilibrium, or the net force equals 0. Plugging in our individual forces and adding them together, we find that tension in the spring scale plus the buoyant force minus the weight is equal to 0, because the weight opposes the tension and the buoyant force. We also know that the weight is equal to mg, or 2 kilograms times 9.8 meters per second squared. The weight of the object is 19.6 newtons. The volume of the object, because it's entirely submerged, is mass divided by density, or 2 kilograms divided by 19,300 kilograms per meter cubed. We get a volume of 1 times 10 to the minus 4 meters cubed. Again, this is the volume of the object, but because the entire object is submerged into the water, then this is actually equal to the volume of the fluid displaced, which will be used in our buoyancy formula. Buoyant force is equal to density of the fluid times the volume of the fluid displaced times g. The density of our fluid, water, is 1,000 kilograms per meter cubed. We found the volume of the fluid that's displaced, which is equal to the volume of the gold cube, 1 times 10 to the minus 4 meters cubed, and times g, 9.8 meters per second squared. We find the buoyant force to be 1.02 newtons. Because we're looking for the reading on the spring scale, we're going to solve our original equation for tension in the spring scale, which is equal to weight minus the buoyant force, or 19.6 newtons minus 1.02 newtons, which is 18.58 newtons. And converting that to a mass, we find that the apparent mass of the piece of gold is 1.9 kilograms, compared to the actual mass, 2 kilograms. Part B then asks us to determine the reading of the bottom scale. The bottom scale is going to read the mass, or maybe even the weight, of the entire setup. We have a 0.4 kilogram beaker of water. We have 1.2 kilograms of water in the beaker, and we have a 2 kilogram piece of gold in the fluid, in the water. But that 2 kilograms doesn't act fully on the scale at the bottom, because the spring scale is providing an additional upward force, or negative 1.9 kilograms on the scale. So adding them all together, we get 1.7 kilograms. So the bottom scale only reads 1.7 kilograms. Problem number 4. A wooden sphere with a diameter of 0.1 meters and a density of 900 kilograms per meter cubed is held underwater by a string. What is the tension in the string? And please note that the density of water is 1,000 kilograms per meter cubed. Pause the video for time to work on the solution. Again, it is most helpful to begin with a free body diagram of our wooden sphere. The wooden sphere has weight acting down, buoyant force acting up provided by the water, and tension in the string, which pulls downward. Because the wooden sphere is less dense than the water, the wooden sphere wants to float, but tension in the string is pulling it down, keeping it from floating up to the surface. So tension's a downward force. Because our wooden sphere is at rest within the fluid, it's in a state of equilibrium, we can say that the net force equals 0. Or, taking into account our individual forces, buoyant force minus weight minus tension is equal to 0. Well, the weight of the object equals m times g, and mass can be written as density times volume. We also should note that the volume of the sphere is 4/3 pi r cubed. Plugging in our radius, which is half the diameter, we get the volume of the sphere to be 5.24 times 10 to the minus 4 meters cubed. For the weight of the wooden sphere, we'll plug in density of the wooden sphere, 900 kilograms per meter cubed, times volume of the sphere, which we just found, times 9.8 meters per second squared, and we find the weight of the wooden sphere to be 4.62 newtons. The buoyant force is equal to density of the fluid times volume of the fluid times g. The density of the fluid, water, is 1,000 grams per meter cubed. The volume of the fluid displaced, in this case, is equal to the volume of the entire sphere, since the entire sphere is underwater. So, we use the same volume as above, 5.24 times 10 to the minus 4 meters cubed, times g, 9.8 meters per second squared, to find the buoyant force equal to 5.14 newtons. Plugging weight buoyant force back into our original equation and solving for tension, we find tension to be buoyant force minus weight, or 5.14 newtons, minus 4.62 newtons, is equal to 0.52 newtons. So the tension reading, or the tension in the string, would be 0.52 newtons. And here's our final problem. A sphere with a radius of 10 centimeters and a density of 2,000 kilograms per meter cubed is suspended in water. What is the tension in the string? Pause the video for time to work on the solution. Beginning with our free body diagram, the sphere has a weight down, a buoyant force up provided by the fluid, and in this case, a tension upward. The tension is upward because the sphere is more dense than the water, so the sphere wants to sink. So the string attached to the sphere is keeping it from sinking, and therefore is providing an upward force. Our sphere is at rest or in a state of equilibrium, so the net force acting on it equals 0. Plugging in our individual forces, tension plus the buoyant force minus weight equals 0. Weight of the object is equal to mg. M can be replaced with density times volume. Density of the object times volume of the object. Because our object is a sphere and we have the radius, we can find the volume of the sphere, 4/3 pi r cubed, which turns out to be 0.0042 meters cubed. The weight of our object equals the density of the object, 2,000 kilograms per meter cubed, times the volume of the object we just found, 0.0042 meters cubed, times g, 9.8 meters per second squared. Weight equals 82.3 newtons. Buoyant force in this case is equal to density of the fluid times volume of the fluid times g. The density of our fluid, water, is 1,000 kilograms per meter cubed. The volume of the fluid, in this case, is equal to the volume of the object, the whole object, which is 0.0042 meters cubed, times g, 9.8 meters per second squared, is a buoyant force of 41.16 newtons. Solving for the tension in our original equation, we find it to be weight minus buoyant force, or 82.3 newtons minus 41.16 newtons, equals 41.14 newtons. So the tension in the string is 41.14 newtons. An interesting practical application of Archimedes' principle and buoyancy is icebergs. Consider the iceberg shown. It is obvious that it floats at the surface, This means that the iceberg must have a lower density than the water that it floats in. This is true because pure ice has a density of 920 kilograms per meter cubed, whereas seawater has a density of about 1,025 kilograms per meter cubed. Typically, an iceberg is submerged such that only about 1/10 of the volume of the iceberg is above water. This can be proven if you understand that the iceberg is in equilibrium and the weight of the iceberg is equal to the buoyant force provided by the seawater. You may wonder what would happen to the sea level if iceberg were to melt, or if all icebergs were to melt. Most people would be surprised to learn that the melting iceberg would have no influence on sea level. The sea level would remain the same even if all icebergs submerged in water were to melt. So how do we explain this? This is because when an object is immersed in a fluid, the fluid exerts an upward force on the object equal to the weight of the fluid displaced. This is basically a statement of Archimedes' principle. An iceberg which is not melted has a weight Wi and a volume Vi. It displaces a weight of water Ww with volume W. But because seawater has a greater density than the iceberg, then Vw is greater than Vi. So it floats, and some of the iceberg sticks up above the water. When an iceberg melts, it has the same weight W, but now less volume because of a higher density. It still displaces the same amount of water because it displaces a weight of water Ww. Therefore, melting an iceberg, which is floating, does not change the sea level because it's already displacing the water. However, if the iceberg were not floating in water, but instead were sitting on a landmass and it melted, it would add water to the ocean, and this would increase the sea level. So icebergs that are already floating in water can melt, and it will not change the sea level. However, if these icebergs are outside of water, they're not already displacing the water, so when they melt and run off into the water, then the sea level will increase.